Welcome everyone to our YHS webinar titled From Global Insights to Local Impacts, Navigating GCMs, Ensembles, Downscaling and Climate Change Assessment by Yaswanth. Yaswanth is a research scholar in the Department of Civil Engineering, Hydraulics and Water Resources Engineering Division, IIT Madras. Yaswanth is working on urban morphological representation in numerical weather prediction models. Now, without further delay, I request Yaswanth to start the presentation. Yaswanth?
Am I audible, Abhinesh?
Yeah, you're audible. Is it possible to open your camera as well?
I think there is having a slight issue with the camera. The drive is not working. So I'll just go ahead with this. Yeah.
Sure.
So, so Abhinesh, my screen is visible to you, right?
Yeah, it's visible. Perfect.
Yeah. Okay. So thank you. Good afternoon, everyone. I'm Yaswanth, doing PhD at IIT Madras. So today I'm going to give a webinar on behalf of YHS on the topic, the global insights to local impacts. So the navigating through global general circulation models, ensembles, and the concepts of downscaling and climate change assessment. So the main motivation behind understanding such concepts of the high resolution weather forecasting or the climate change. So what is a probable rise in the extremes or the frequency in the extreme weather events is because the recent decades, especially in India, the flooding frequency has increased and it is causing huge loss of lives and damage. So for example, if we consider Bombay 2005 floods, around 950 mm of rainfall happened in a day. So it is nearly 70 to 80% of average annual rainfall that happened in a day. And similarly, if we consider Chennai 2015 floods, similarly, 60 to 70% of the annual average rainfall has happened in a single day. So this clearly shows that a large amount of rainfall is happening within a very short duration, so which is leading to floods, as well as the huge loss to the economy. So in this context, it is very important to have a reliable weather prediction model. So if we have a reliable forecast at 1 or 2 day lead times, we can advise policymakers and engineers what decisions to be made. And at the same time, if we have an understanding of how these extremes are going to change under the global warming, that is under the coming centuries, we will have a better preparedness, better engineering infrastructure. So when it comes to weather and climate, as an introduction, I just want to separate the two things to make better understand what is the difference between the weather and climate. So the weather is what we see at particular time of the atmosphere at current time. Say, for example, what is the weather for the next 3 days? What is the state of the atmosphere for the next 2 days? Or what is the state of the atmosphere at current at a particular location? But when it comes to the climate, it is generally considered as an average of the weather patterns for very long years. Say, usually we say 30 years or more. So weather is what we expect in the atmosphere at today or tomorrow or in the next 7 days. But climate is something, the average property for a very long duration. The complexities that exist in the weather prediction model is, so the weather prediction model is an initial value problem. So you change slightly the initial values that you are providing to the model. So atmosphere is a very chaotic system. It just gives out a different rainfall, different temperature, etc. So weather is a very complex to model, and it uses a lot of complex partial differential equations. So the two main conditions that we require in the numerical weather prediction model is the present atmospheric conditions, that is the initial values that we are providing to the model, and what loss it is considering to predict the atmosphere in the next day or in the next 2 days or 3 days. And it is also important at what resolution you are providing the forecast. For example, a user may require forecast at 1 kilometer resolution, or some users may require forecast at 10 kilometer resolution. So in urban hydrology, a user may be interested to know what is the rainfall at every 1 kilometer pixel. But when it comes to rural hydrology, user may be getting satisfied even with if you provide a forecast at every 20 kilometer spatial resolution. So the main issue in the weather prediction model is its sensitive dependence on initial conditions, so which we famously say as the butterfly effect or the chaotic system of the atmosphere. So a slight change in the input data can give a different spatial location of the rainfall or a different amount of the rainfall. So we need to be very careful when providing the initial conditions to the atmospheric model. So this plays a very, very huge role. So, for example, considering the spatial variation of the rainfall for Chennai 2015 flood event, so this map shows the animation of the radar rainfall intensity values on the December 1st rainfall event. So I have shown here to make better understand the spatial variability of the rainfall and the intensity of the rainfall that is happening. You can see clearly few pockets of the Chennai city is receiving very high rainfall when there is very less amount of rainfall or no rainfall in other regions. So when you are the requirement here is to predict the weather at a very high resolution to better understand which areas are most probably to get the rainfall or which areas are least probable to get the rainfall. So in a nutshell, a numerical weather prediction model will be getting initial and boundary conditions from a global numerical weather prediction model. So to provide initial and boundary conditions, I will be taking the boundary conditions from a global forecast system, which will provide a coarse resolution. But my major aim here is to predict the rainfall at very high resolution at the region of interest. The reason why the global NWP models will be providing at coarse resolution is they typically provide a 25 to 30 kilometer resolution, because running such a complex model at very high resolution is having a very high computational burden. But as a researcher, I'm more interested to know what is the probable maximum rainfall that is going to happen at the region of Chennai. So I will take a regional climate model. We say it is regional because we are concentrating on the domain of interest, that is a region of interest. And I would provide the boundary conditions and initial conditions from a global model to the regional model, and I will simulate it very high resolution. At high resolution, the importance is the model can process the topographical variations such as elevation, land use, land cover, urbanization, etc. At coarse resolution, all these properties cannot be captured very good. So once the rainfall is predicted at very high resolution, I can provide that as an input to the hydrologic modeling, and I can give the flood or the discharge that is going to happen in the river in the next 1 day or 2 days or 3 days. So the main complexities that exist in the models is the parameterization. So to understand better, for example, the cloud resolving scales typically happen at sub-kilometer scale or even at less than 4 kilometer scale. But we run models typically at 10 kilometer scale or 4 kilometer scale or 1 kilometer scale. So if we consider the main properties that are happening within a weather model is like, for example, solar radiation, scattering by aerosols, or cloud updraft, downdraft, all these are happening in very, very minute scales. So the model cannot resolve these kind of properties. Hence, what the researchers' approach is to parameterize them. To parameterize in the sense we give certain values to the updraft speed of the cloud or downdraft speed of the cloud, and the model will not resolve using mathematical equations, but the parameters will take care of it. So when it comes to the parameter values that default the model has, those parameters play a very key role in predicting the temperature and rainfall for the next few days. So a typical complexity that exists in any numerical weather prediction model is we have different schemes such as cumulus scheme, which takes care of cloud updrafts and downdrafts, and the microphysics scheme, which takes care of the cloud nucleus, the number concentration of the droplets, whether the cloud droplets are in ice form or liquid form or frozen form, and the radiation effects, that is such as incoming solar radiation and the outgoing solar radiation. So each physics option plays a very key role in predicting rainfall at very high resolution. And the researchers and scientists have developed different schemes to take care of all this physics parameterization. So typically, when I consider a numerical weather prediction model, if you see this is the Chennai city. So what I'm essentially doing is I'm concentrating on a domain size where the boundary conditions are provided to the outer domain, which is at, say, for example, 9-kilometer resolution. And again, the output, the input to the innermost domain comes from the outer domain, which is at a 3-kilometer resolution. So typically, the numerical weather prediction models at current stage, if we have a better computational facility, we can go for high resolution. But typically, we should understand that these cannot be run with the normal systems, but we need some kind of HPC or high computational power to run in a parallel mode. So when it comes to urbanization, to incorporate urbanization into the model, uh, there has been recent developments in urban canopy models. So these urban canopy model coupling to the weather research forecasting model or numerical weather prediction model is highly important, because if you typically see the cross-section view of a Chennai city, in the right side figure. So the winds that are coming from the ocean or the sea reaching to the city, they can rise around the buildings, pass around the buildings, and due to the radiation changes, due to the construction of roads and buildings, the local climatic process in the urban region can change. So in order to capture that microclimatic change process, because they may have impact on the location and the temporal distribution of the rainfall. So essentially, what we do here is we couple the urban canopy models with the numerical weather prediction models, so that the urban canopy models will take care of the fluxes that is coming from the ground. So a typical example to show the initial and boundary conditions from global model is the NCEP, that is the National Oceanic and Atmospheric Administration. So they provide initial and boundary conditions. And so these are the forecasts available for the entire globe at 25 or 30-kilometer resolution. So I will be selecting these data and provide that as an initial and boundary condition to the numerical weather prediction model at the region of interest. So the recent research is concentrating more on representation of detailed urban canopy models or urban morphological representation. Say, for example, the cross-sectional planning of the buildings, roads, etc., can change the surface net radiation, sensible heat fluxes, and latent heat fluxes. And these can have a huge impact on the location of the rainfall or the temperature of the city. So this local climatic zone classification of cities is coming into the picture. So what essentially we do in this local climatic zone classification. So instead of representing the land use land cover just as an urban region or low intensity urban region, we go for what areas are actually having compact high rise buildings, what areas are having compact low rise buildings, dense trees, scattered trees, etc. So when the model understands the spatial variation in the land use land cover in much better way, there is a chance that we may predict the better spatial location of the rainfall with good accuracy. So the necessity of the urban canopy model in any numerical weather prediction is to better capture the wind profiles as well as the radiation fluxes. So for example, if you consider a weather research forecasting model, we can couple the weather research forecasting model with single layer urban canopy models and multi-layer urban canopy models. So when we couple the urban canopy models, the model is able to capture better the drag properties of the wind, the radiation fluxes from the surface, and the wake diffusions that is happening within the buildings, and the radiation, the cooling or heating due to the building profiles or the road alignments. So essentially, the boundary layer is better simulated from the numerical weather prediction model. Once the boundary layer is better simulated, I may get the better updrafts and downdrafts to the clouds and give a better forecast. So for this webinar, I just followed a simple example representation at this point of time to show the complexities that exist in numerical weather prediction model. So suppose if I want to predict rainfall at the innermost domain is my interest. So as I mentioned earlier, the complexities that exist in any numerical weather prediction model is simulating the boundary layer, microphysics, cumulus schemes, which takes care of the cloud updraft and roll drafts. So there are different schemes from complex to simple schemes to run the model. So these combinations are similar to explain in a simple way. For example, if we consider any hydrological model, so we have different ways to calculate the runoff. So we use SCS curve number method, or we use green ant or Hawthorne to quantify the infiltration. In the same way, we have different methods here to calculate the fluxes from the boundary layer, the microphysics, and the cumulus schemes. So which combination is essentially going to work better is also depends on the region of interest. So sometimes the domain may be inside. So for example, you're simulating the weather for Hyderabad city. A different combination may work better. A different domain configuration may work better. But Chennai is a coastal city, so again, it works better for any other combination. Again, if you go for Bombay, it is highly influenced by the southwest monsoon, unlike Chennai, which is experiencing the northeast monsoon. So it is important for the user to decide which combinations are working better through sensitivity analysis. So typically, the output from any numerical weather prediction model will be at high resolution if the user is deferred. So this is a GCM, that is satellite estimate rainfall, which is interpolated to 1 kilometer resolution. So essentially, these are the different outputs from the different model combinations that I have shown in this slide. So you could see the rainfalls, few combinations of simulated very high rainfall in the sea region, and in the land region, few of the combinations were able to predict more rainfall. So this is all because of the different characteristics that are existing in the physics combinations. So different configurations use different properties. So we do error calculations here with the observation. So this is observation, and we try to find what are the best combinations that is matching closer to the observation. So for example, if you consider again another domain configuration, that is with horizontal resolution 9 kilometer and 3 kilometer, it failed to give a good rainfall amount for the next day. So these simulations I'm starting, the rainfall has happened at 1st December. I'm giving the boundary conditions at 30th November to see what is the rainfall that I can forecast for the 1st December. So for this domain configuration, the model is not working good, and it has shown less rainfall and shifted away from the coast. So this is also one of the complexities with the numerical weather prediction model. So the domain configuration, the choice of physics options, everything plays a very crucial role. So once I have the rainfall forecast for the next day or next 2 days, I can use that as an input to the hydrological model to predict the discharge that is coming into the river. So with few of the best combinations that I have found, so this is a predicted river discharge. So once I could predict with higher confidence the inflows to a reservoir or the river discharge, so I can guide the engineers when to release the water or how much quantity to release the water. So essentially, there are a lot of applications once we have a rainfall predictions with higher accuracy. So the reason why the urban canopy models are better predicting the rainfall location and the timing is because they're able to see a very good amount of close values with the urban canopy model with a rain gauge graded data compared to without urban canopy model and the old land use land cover. So it is also important in numerical weather prediction models to represent the recent land use land covers and couple it with canopy models. So essentially, if we see the convective available potential energy, the urban canopy models are simulating the higher convective available potential energies. So in the atmospheric science, if you see the higher Cape values, there is a potential for higher rainfall. So the lower the SIN values, there is potential for higher rainfall. So essentially, the urban canopy models can be seen with higher Cape values, lower SIN values. So the path for the numerical weather prediction is just focusing on what is the next 2-day rainfall or 3-day rainfall, and the complexities exist that we cannot forecast the weather with higher reliability after 3 or 4 days because of chaotic system of the atmosphere. So it's very difficult to say what happens the next 7 days with the weather model because of the chaotic system of the atmosphere. But when it comes to the climate models, we run the models for centuries to see what is the state of the climate in each 30-year period. So when it comes to a climate model, it considers many components in a three-dimensional grid. For example, it considers the ocean, land, biogeochemical process, etc. And with recent advancements in the computational power, it is simulating at higher resolution, considering the chemical exchange between the living organisms and the atmosphere also. So the scientists are introducing new components into the models, and that these climate models, since they are run at very longer time duration across the globe, so they are typically maintained at coarser resolution, because running a climate model for 100 years, 200 years require huge computational power and time period. So running at 10-kilometer resolution a climate model for entire globe is impossible with the present computational. So typically the climate models run at 100-kilometer resolution or 200-kilometer resolution. So one small thing we should notice when we run the climate models understanding is, so the weather is an initial value problem. So after 3 days, 4 days, the model may not predict the right amount of the rainfall. It just deviates. But the climate, we are not focusing on what is happening in the next 2 days or what is happening at 2030 Jan 1st or 2040 Jan 4th. We are just focusing on what is the average climatological state in the next 30 years or from 2060 to 2090. So essentially the models do not say exact date of that heavy rainfall happens, or the models will help us to understand how the frequency of the extreme events are changing, or the frequency of higher temperatures are changing, or the heat waves, etc. So we cannot compare climate models directly day to day with observations, which we should keep in mind. So the basic laws that climate models typically follow is the first law of thermodynamics, that is energy conservation in a closed form system, the Stephen-Boltzmann law, and the famous the Navier-Stokes equation. So solving these complex equations requires a lot of time. So that's why they simplify few of the procedures and run at coarse resolution across the globe. So a typical example code in any climate model looks like this. So they considers land, the moisture that is coming from the land and the ocean, and the leaf area index, other chemical properties, etc. And they do run using the Fortran codes with a long, each will be having around 18,000 to 19,000 runs of the code. So this essentially I have shown here to understand the complexities that exist in running a climate model for a long duration. So the spatial resolution of the climate model plays a crucial role. So most of our hydrologists require the rainfall data at high resolution, not at 100-kilometer or 150-kilometer resolution. But typically the global climate models or the general circulation models provide at very coarse resolution. So here comes the concept of downscaling, that is increasing the coarse resolution outputs to fine resolution outputs. So if you see the way back, the climate models from 1990s to 2015s, with advancements earlier when they have given the output at 500-kilometer resolution, now the scientists were able to run with available computational power and providing the outputs at 110-kilometer resolution. So even then the 110-kilometer resolution is very coarse when you see rainfall that should be provided as an input to the and so one important thing to notice is, so if you see the increase in the spatial resolution of a model, at least by a factor of 2, you need 10 times more computing power. So this is where the scientists limit their model runs at a particular spatial resolution.
Yaswanth?
Yeah, am I audible, Abhinesh?
Yeah, yeah.
Yes. So just 1 second. I think it's not responding. So if we come across the decades, the scientists have developed the climate models considering various complex processes too. So, so earlier decades, we have considered the aerosols and biochemical cycles, and later now the scientists were able to see the inputs of ice sheets and vegetation interacting and carbon fluxes, etc., into the global climate models. So one important point to notice when we see the output from climate models is, so the climate change can happen due to external factors as well as the internal factors that are happening in the earth. Say, for example, the volcanic eruptions can release a large quantity of aerosols and it can cool the atmosphere for the next 2 years. So this has nothing to do with the human activities, but we are interested to know in both ways what the natural factors that are causing the change in the temperature or any other climatological pattern changes in the Earth's atmosphere, or else what is the human contribution. So for that reason, what scientists do is they run the climate models in both ways. So cut down all the CO2 emissions in the models and just give the volcanic eruptions and sunspots changes. So due to the sunspot cycles, also the climate changes. So they see only natural factors and run the models. And in the second step, they use all the human induced factors that like greenhouse gas emissions, etc. And they run again the models. So this typically makes us to understand what is the contribution from the humans to the change in the climate. So for example, if you see the rise in the temperature over the past 50 years, so the black line shows the observed, and with the natural forces, that is only due to the volcanic eruptions and sunspot changes, the temperature is in the blue shade. But if you see with the human contributions, the models that have taken greenhouse gases also into the account has followed the pattern similar to the observations. So indicating that there is an anthropogenic influence on the Earth's climate system, and thus the temperatures are on the rise. So when we download the climate model data sets for our analysis, we should understand what is the CMIP, that is coupled model intercomparison project. So across the globe, there are many research institutes that run the complex mathematical models to simulate the climate for the past and for the future. So scientists can take their own ways to project the future climate projections. Say, for example, I may be interested to know what is the future land use, land cover, population growth, or industrial growth, and I may run the model based on my own inputs. So different groups may give different inputs and run the model. So we cannot compare different models that are currently available at the globe. So for that reason, scientists have gathered and established these CMIP groups so that they provide instructions to the scientists and researchers what they should consider before running the model for a very long time period. Because these models are running for with a very complex computational burden. So there should be a guidelines to make the researchers understand that, okay, this should be the input to the model before running. So you'd say 4 times more CO2, that is carbon dioxide, into the model and run for the next 100 years. So they're setting a guidelines to the scientists. So the recently the CMIP 6 is the last meeting that has happened, and they have delivered some global circulation model data to the end users. So if you see CMIP 6 scenarios, the CMIP 5 has been delivered around 2012 or 2013 year, and recently 4 years back, CMIP 6 group has released the new set of models. So this is a historical CO2 emissions, and we run the scientists run the climate models into the future, assuming different release amounts of CO2. So there is a high emission of CO2 and there is low emission of CO2. So they try to run the models with different emissions, thinking about the optimistic ways and pessimistic ways to understand how the climate is responding to different emissions of the greenhouse gases. So if you see the examples of models or the countries that have developed different global circulation models. So these are the different global circulation models available across the globe. So the reason why we choose all the models sometimes is to understand, because some models may fail to predict better. Some models may fail to predict the historical changes in the rainfall or temperature, while some models may give a better prediction. So it is essential to understand all the models to see their performance in the past, and we usually assume they perform better in the future. As I mentioned previously in weather research forecasting model, the complexity is existing say if you change the boundary layer scheme or physics options or anything, the output is essentially changing. The rainfall can have a spatial shift or temporal shift. So that's the reason different models are run with the different initial conditions. So a model which can better capture may be used for better projections. So when it comes to ensembles, the terminology we use to run the same model with different initial conditions or different physics option. So as I've shown 12 different combinations of WRF output rainfall, the scientists also run their models with slightly different initial conditions, slightly different physics combinations. Sometimes they run model with 3 to 4 different boundary layer combinations because they are the complex simulations which are highly dependent on the cumulus options and microphysics options. So they try with different. So for example, you run the hydrological model with SCS, Cohn-Emmer method or Greenamt or different, and to see what is the discharge. So they also typically run with different. So that's how the ensembles are produced. So a single modeling group can run the same model 10 times or 50 times with different initial conditions and different physics combinations. So that's why they have given a notation called, so when we download the data set also, so this is important to see which combination from each model we are selecting. So the model has been run with different initial conditions or different physics combinations. So these details are already provided in CIMIP6 website. So, and it is important before we use, we have to have a check on which ensemble member we are using actually. So if typically the variant label I have shown here example is R1, I1, P1, F1. So when a researchers or hydrologists want to download multiple GCMs, so the Access EM2, for example, this GCM may have 50 different models within it, like another variant label may be R2, I1, P1, F1 or R1, I2, P1, F1. But when you choose different models, we try to stick to the same variant label because we can't select 50, 60 models at a time for each model. So we want to reduce our computational burden, but we take care that almost the same variant label is selected from the each model. So how to compare the climate models with observations? So not only into the future, the scientists also run the climate models from 1850 to 2015, say for example to the past, which we call them as hindcast. So these simulations can be compared with the observed climate. And here the caution is, as I said earlier, we cannot go back and see like a 2005 Bombay flood happened. The climate model also shows the same amount of rainfall. No, it's not that. The climate models are just run with the greenhouse gas projections or the natural forcings. In a 30-year period, if we see the frequency of rise in the extreme precipitation or the positive trends that are observed in the temperature, the models also should capture such climatological patterns and distributions. So we don't go for exact to exact match when we are comparing the climate models. So this is a typical example as I provided before, but this is showing the temperature anomaly. So the positive anomaly shows the rising temperature. So I'm not comparing the day-to-day or something, but I'm just comparing the climatological pattern, and I'm seeing whether some of the CIMIP6 models are well capturing the rise in the temperature that is seen in the observations. So as I've discussed earlier, the main complexity existing in running these models is the parameterizations. So typically the climate models which are run for hundreds of years also exist with the same parameterization issues. So which parameters you are using, what schemes you are using, the outputs again depend on that. So we essentially try to focus on errors in the climate model outputs because we cannot directly use a climate model output of rainfall or temperature as an input to the hydrological model. So that is not right way because we need the data at very high resolution, and also we need that climatological state to match with the observed climatological state. So if we typically see the errors usually from the climate models, that can happen due to unrealistic large scale variability. Say for example, the atmosphere is influenced by jet streams, El Nino, La Nina, etc. So the models may not capture well all these properties similar to the observations. So the errors can exist due to that. Or there can be unpredictable internal variability. So the internal variability of the climate usually we characterize for 10, 20 years. Say for example, the climate model has started running from 1860. You are comparing your observations with 30 years from 1970 to 2000. The climate model may have 10 or 15 La Nina events, but your observations may have only 5 or 6 La Nina events. So there is nothing wrong with the climate model, but the internal variability, that is the teleconnections or some other things, may make the comparisons worse. So that is the reason we go with ensembles, that is multiple climate models, as well as within climate model, different runs, different initial conditions, so that the outputs can be delivered with higher confidence. And the last one is errors in convective parameterizations. So that's what have been discussing earlier, how the parameters are being handled by the scientists in the convective or microphysics or what boundary layer, etc. So all these errors also essentially propagate into the outputs. So if you are a water engineer and you are asked to construct a hydraulic structure or anything, so we are focusing on the local or region of interest, but our global climate models are providing the data at a coarser resolution, say for example 110-kilometer resolution, but we are not interested in that. We are interested in high resolution, but due to the lack of computational power currently, so the models are able to show only the outputs at 100 or 150, and some models at 250-kilometer resolution. So the engineers need the data at very high resolution, but not at the coarse resolution. So here comes the definition of the downscaling that bridges the gap from the large-scale global circulation model for assessing the local impacts. So for example, if you typically look at a general circulation model, it is at very coarse resolution. So if I consider my study area of interest is this, the only 4 grids are falling into the area, but I need an output at very high resolution, which is unavailable. So now I do the process of downscaling, that is bringing the coarse resolution to the fine resolution. And essentially the fine resolution data I can provide as an input to the hydrological model to see what is a probable chance of flooding or probable chance of exceeding the peak discharge, etc. So to do this downscaling, there exists, so broadly they are classified into 2 types, that is statistical downscaling and dynamical downscaling. So dynamical downscaling is similar to running a regional climate model or regional weather prediction models kind of things. Say for example, WRF or any other NWP model. So dynamic downscaling is again a kind of simulating the atmospheric process at high resolution. But when it comes to statistical downscaling, it is just a kind of mathematical technique where we use some kind of regressions or neural networks, etc. We need not use any weather models for doing the statistical downscaling. So in terms of computational power, the statistical downscaling is with ease. So you can write your own codes. So your own neural network course or linear regression or multiple linear regression course. But when it comes to dynamical downscaling, again, you need a numerical weather prediction model kind of models. And it is complex to handle because you simulate at high resolution, computational power is required. You need months and months to run the models. But the dynamical downscaling handles the physical process because the models are working with the physics of the atmosphere. But the statistical downscaling is your own mathematical model. We assume the regression equation is capturing better, and the same equation can capture better in the future also. So to better understand statistical downscaling, so suppose, so consider this box as my region of interest, and the data is available at very coarse resolution. So I want to know the rainfall climatological pattern at this box into the future. So what essentially I do, I take the large scale atmospheric variables surrounding this box to some region of influence. I establish a relationship between rainfall and these predictors. So essentially we call what we are determining, we call it as predictant. Say for example, the Y here may be rainfall, and we assume this rainfall is a function of several predictors. So the predictors can be mean sea level pressure, temperature, wind speeds, or wind convergence, divergence, vorticity, etc. So once we establish this relationship, we tune the parameters so that the statistical model is best fit with the observations. And these predictors are available from the GCMs at coarser resolution for the future. For example, say 2030 to 2100. We provide them as inputs to the model, and we get the value of the predictant for the future. So one important assumption here is we are training this model for the past using the observations, and we assume this relationship holds constant for the future. That is a stationarity assumption. So this is one of the assumptions in the statistical downscaling. And to show a simple example, the precipitation can be a function of these variables. So in the statistical downscaling, essentially I use some kind of regression or neural network techniques to establish relationship with precipitation with these independent variables. And these variables are available for the future. So I give them as an input to the model and I predict the precipitation for the future. So you develop the statistical relationship between observations and the model. One important thing we should notice is always we consider at least a minimum of 30-year recent data to establish that relationship, because we are concentrating on the climate, not weather here. So we first derive the statistical relationships and then we apply the same statistical relationships into the future. Say, for example, 30 years into the future, 2030 to 2060, 2060 to 2090, the same relationship is being used for the future. So to establish a relationship of regression or neural network or anything is a computationally least burden. But when you go for dynamical downscaling, you have to run weather models for hundreds of years or 30 years or 40 years, which is again a high computational power. So this is one of the advantages of the statistical downscaling. The recent paper has suggested several statistical downscaling regression techniques. So they have used from neural networks to simple multiple linear regressions. So the interested users can go through this paper to better understand the details of the statistical downscaling. So when it comes to the dynamical downscaling, so suppose if this is a region of interest. So as I told earlier, the models require initial and boundary conditions. So for the climate model, it is not an initial value problem, but boundary value problem, because we are running the climate model for the long period. So initial values are not important here, unlike in the weather model. So we provide the boundary conditions that are coming from the global circulation models that are already available at 150, 300 kilometer resolution. And essentially in the downscaling, we are focusing on developing high resolution precipitation or temperature. So I will run a regional climate model, say for example, weather research forecasting model. So that needs boundary conditions. The GCM will provide the boundary conditions and I will run at 12 kilometer resolution or 4 kilometer resolution. Whatever the resolution I want, I will run the regional climate model to get the values for the future. So one important thing to notice is the regional climate models are based on physics of the atmosphere. So they can better capture the land-sea contrast or the local orography or small scale features such as the urban regions, etc. So, but your statistical model, which is just developed on the large scale atmospheric variables, may not be able to capture this physical process that is inherently happening within the models. So this is one of the advantages of the dynamical downscaling. So one who has high computational power can go for the dynamical downscaling. So one interesting thing always in climate change is the bias correction. So although we do dynamical downscaling or statistical downscaling, or even from the climate model outputs, they may not exactly match with the observations. So may not match with observations here, I mean is the probability distribution of the observations. So as I told, we do not directly match the climate model outputs with day-to-day observations. We match with the probability distributions, like how well the distribution of rainfall from the model is matching with the distribution of observations. So the distribution is not matching. We have several techniques to make the distribution to match. So this terminology is called bias correction, where we adjust the values of the model outputs so that their distributional properties such as mean, variance, etc. will match with the observations. So two simple techniques always that comes in bias correction is delta change and qualitative mapping. So to better explain in a very simple way, I have taken the delta change method. Say for example, I have a GCM observations, around 10 to 11 observations, but typically remember if I'm correcting at monthly, I need 30 such observations from both GCM and as well as observations. But here for brevity, I have just taken these values as a sample. So if you see the mean of the GCM, the temperature is 24.57, whereas from the observation, the mean is 25.24. I'm not directly comparing 22.3 with 20 or 24 with 23 because that's what essentially the climate models do not do. We are just focusing on the distribution properties. So there is a bias in the distributional properties. So there is a 0.68. It is under predicting. The models are under predicting 0.68 when I consider the mean. So what essentially I do, so these are the GCM values. I add this 0.68, the mean bias, to every GCM value, and I get the new GCM values. And essentially now if I calculate the mean of the GCM, it is 25.24, which is equivalent to the mean of the observation. So although the exact match is not there, here I'm trying to match the climatological state. So if you see, the mean is adjusted. But if you see the variance, that is of standard deviation or any other property, it might not be matching because it is a simple bias correction where I have adjusted only the mean, because I found the error in the mean and I try to adjust the value so that the mean will match. So there exist higher bias correction techniques, such as instead of not only mean, I will match mean and other every distributional property of the GCM with observation. So for example, consider this. So this is the GCM values before bias correction. So this is a cumulative probability distribution, which actually tells about the exceedance probabilities. And these are the observations. So before bias corrections, if you see the distribution of the GCM, it is not matching with the observation. But after mean bias correction, they are closely coming to the observations, but not exactly following the observations because I have adjusted only the mean, but not other statistical properties. So especially if you see the extremes, they are not matching. So here comes other techniques such as quantile mapping, where I try to adjust the entire distribution of model with respect to observed. So what essentially I do, suppose select a temperature value, the model distribution at a particular probability level is showing, for example, 50 degrees Celsius, but the observed is only 40 degrees Celsius. So I make my algorithm in such a way and write it so that essentially the distribution of the model matches with the observation. And we tell now the distributional property of the climate is better than the original GCM. So this is essentially trying to adjust the distributional property of the climatological values developed by RCMs or GCMs with observations. So we try to forcefully adjust the values, and usually we test this. Say we establish this algorithm for 30 years data, and we test for 10 years of observation data, and we see whether really it is working or not, whether the distribution is matching with observation, like a kind of calibration and validation, and we see that this is better technique. So what essentially the quantile mapping does, so we have observations, we have historical climate model output, and we have also future climate model output. So essentially the main goal is how to adjust the future climate model output so that it matches closer to the reliable values. So if we consider the future, for example, a precipitation value at a 0.9 cumulative distribution function. So this has a cumulative value of probability distribution of 0.8. But if you see the observations and the raw historical model, there is a difference. So there is a bias. So the blue line is a historical model and the black line is a historical observation. So the blue line is not matching with the black line, indicating that there is a bias in the model. So how to adjust the bias for the future? So for a future precipitation value that is given by the model, I will see what is the bias in the historical, because in the historical I have observation, so I can compare. And that bias, I will try to adjust for the future value at the same quantile level. So essentially, if you see, this is a kind of adjustment to the curve. So the future values based on the identification of errors in the historical with observations. So you try to adjust the historical model outputs as well as the future model outputs, and essentially saying the mean variance and all the distribution properties are matching with the observations. But what essentially the recent researchers have found is around 6 to 7 years back, the quantile mapping, which is very, very widely applied, has an inflation technique. So it can artificially corrupt the trends that is happening in the models. And if the model is showing 20% positive trend, because of quantile mapping, the inherent algorithm is showing 40% to 50% higher trend after corrections. So which is not actually shown by the GCMs. So they suggested that it is better to use quantile delta mapping rather than quantile mapping, which actually corrects at the same quantile levels instead of going for the upper region values. So how this correction happens is, say for example, you have again the black line that is observations, the blue line, the raw historical model, and now the green line is the model value, the red line is the corrected future value. So how I am correcting these values? Say for example, I have the raw historical model, the raw future model. Now I know the changes that is happening at this level between the historical and future. So this is the GCM historical, this is the GCM future. So I know at a particular 0.8 CDF level, what is the change that is happening between the future and historical. The same change I will apply at the 0.8 level with respect to the observations, and I will say this is the future expected GCM climatological distribution. So instead of going to the above values in the historical and correcting, I'm doing at the same quantile level, all the corrections. And essentially, the findings have proven that this method is better giving the trends observed in the GCMs rather than the quantile mapping. So in summary, at what we have discussed is we have global climate models and regional climate models. So the regional climate models essentially focuses on the region of interest, and we wish to run at very high resolution if we have computational power and storage capacities. So these actually the regional climate model runs considering the atmospheric physical process. But when it comes to statistical downscaling, they usually consider some kind of regression techniques or our own statistical methods to establish. They may not consider the physics of the atmosphere well, but they're computationally less burden. And the main motto of this downscaling to higher resolution is, or bias correction is, to provide the high resolution input to the hydrological model to have a better predictions. So in terms of conditions, we have statistical and dynamical. So if we are having the resources for our projects, say well-established computational power and the storage capacities, because sometimes the dynamical downscaling outputs, we need terabytes of capacity to store even the output. So an analysis is much more complex. So if such conditions are available with us, we go for the dynamical downscaling, or else we go for the statistical downscaling. So within the downscaling, what I have discussed here is the spatial downscaling, that is bringing the 100-kilometer resolution to 25-kilometer resolution or 10-kilometer resolution. And we have essentially the temporal downscaling also. Say, for example, you have the future GCM data at daily scale, but you may be requiring the hourly rainfall data. So you go for some kind of temporal downscaling techniques to disaggregate the daily data, the hourly data. Yeah. So thank you.
Thanks a lot, Yashwant, for a wonderful presentation. Now I request Tejasvi to carry forward with the discussion. Tejasvi, are you here? Okay, in the meanwhile, yeah, if anyone has questions, they can raise their hand and or they can add their question in the chat. Tejasvi, floor is yours. You can carry the discussion.
Thank you, Vinesh. Yeah, if anyone has any questions, please raise your hand.
Hello. I'm audible, Yashwant?
Yeah, you are audible.
Yeah. Thank you for the great presentation. Really, I've enjoyed the presentation. And then I've got to learn many things from this presentation. I have a quick question. The purpose of this regional circulation models is, as you have mentioned very clearly at the beginning, we want the data in particularly for these urban cities where at the high resolution, right? And you have clearly mentioned in the summary slide that if there is no historical data for calibration, how to proceed further? Like, what is the reliability of this model? Or what's the uncertainty with the predictions, for the next 3 days?
Yeah, I actually, with the growing degree of the satellite data and other things, we are not devoid of the historical data. But if we cannot have the comparison with observations, then it would be a very difficult process to say which combination is actually giving a better result. So at least in terms of not having observations from the stations or the physical measurements, at least we usually compare with the satellite estimates, because these days there are different satellite products available at high resolution. So at least with the near, but even they have the biases. It is always important to consider the bias before direct comparison. But so without observations, we cannot conclude that which combination is giving the better thing. Am I clear to you?
Yeah. Thank you, Yashwant. So that's why, I mean, in real terms, like when we go for the real term predictions or for the next 3 days, and then to what extent can we use this recent advancements? Yeah.
Yeah, the
So
recent advancements you consider, it will be in form of the data assimilation. So assimilate more observations at the initial stage, like for example, if you have the real-time soil moisture or any other cloud radiance data, so the model will get better initial conditions so that it gives a better output. So and one more thing is, we use typically do not depend on single simulation, but different combinations of physics options we do give. So for example, if I run 10 models, and out of that, if I say 5 models have predicted a rainfall greater than 100 mm. So then I will say there is a 50% 50% probability that there is a chance of happening rainfall greater than 100 mm. So we always now go for the probabilistic forecast, like 70% probability or 80% probability.
yeah. Thank you. Looking forward to connect with you. Yeah. Thank you.
Thank you. Thank you.
Yeah.
Abhinay, sorry to interrupt. I think just I'll take a 1 or 2 minute time to show. Maybe a few of the users may be interested to know how to download the GCMs. Just it takes 30 seconds time.
Yeah.
So
Okay,
because
okay.
that is one of our lines at the end of the abstract to show how we usually download.
Yeah, sure, Yashwant. We have a hand raised, so
Yeah. Sure.
we'll take this question after you.
Yeah. Fine with that. Yeah.
Yeah, please go ahead.
Hello.
Yeah, you're audible, Samnan. Go ahead.
Yeah, sir, if you want to select the best GCM for a particular regional area, for example, a city of a particular state, then what will be the general procedure to select the best GCM for that area? Thank you.
So here I would like to bring 2 points. A GCM which is not performing for the past, we should not consider that it may not give reliable future projections. So there is a saying regarding this. But even then, if you want to minimize the number of GCMs, you can find out the distribution comparisons, as I have shown you some CDF comparisons. You can use error metrics on climatological basis, like a monthly climatological basis or daily climatological basis, what you are actually using. So you can use root mean squared error or any other error techniques to understand the correlation coefficient to root mean squared error, all these error techniques to understand the errors in the GCMs. And essentially you can give weightages to the GCMs. Like if a GCM is performing so good, so you have inverse relationships here. The least the root mean squared error, the more weightage it goes to a particular GCM. So essentially you will be giving weightages to the each GCM based on the performance, and you will be getting a single value. Or else, out of all the 35 GCMs that are available from the CMIP 6, you can discard the GCMs that are not giving good matching with the climatological region of what you have. So you will compare here different things like interannual monsoon variability and how the temperatures are being forecasted for the winter, summer, or uh, they're able to capture the interseasonal and intraseasonal variabilities, etc. And one more important thing to do is, as I've explained in bias correction, we try to forcefully adjust the GCM values with the observations in terms of distributional properties. So one important thing that recently they have produced a paper, and they have stressed that it is a forceful kind of adjustment. So before that, you just try to focus and see whether the GCMs are able to simulate even the large scale atmospheric variables also. Like in your region, the weather may be impacted by the constant settling of a jet stream, or there may be changes in the 850 hPa upper level atmospheric variables. So in the last 30 years, whatever trends you are seeing in the observations, whether the GCMs are able to capture realistically at least to the near to the trends, then you choose such GCMs and apply the bias corrections.
Okay, so before bias correcting the GCMs, we have to check whether the GCM is working with the observations or no, right?
Yeah,
So,
yeah, you have to check with that.
and a root mean square method is one parameter for deciding the best GCM, and there are many parameters to decide. So we have to make sure what are the geographical and topographical parameters of our area, right? So uh,
Yeah, essentially these are some of the parameters which you error metrics which you calculate to say, okay, this GCM is better capturing the observation, so I'll give importance to that particular GCM.
okay, thank you very much, sir. Thank you.
Yeah, so we have some questions in the chat box. If let's start with Nitin Singh. Would you like to ask this question yourself, please? You can turn on the video and ask. If it's not possible, I'll read the question. So Nitin asks, are GCMs, can they be considered as a subset of RCM? Yashwant.
Sorry, the question is not clear to me, but if I understand what actually he mean to ask this, the GCMs are not subsets of RCMs. So we cannot say the word as subsets of RCMs. So the GCMs are generally the general circulation models which are run across the globe, but the RCMs will take the boundary conditions from the GCMs and run at very high resolution, since we are focusing only on the region of interest, say for example, very small domain like, or a region of country like India. So we take the boundary conditions of the coarse resolution GCM and run the RCM at high resolution.
Yeah, so next question is by Suresh Devaraj. Suresh, would you like to ask the question yourself? Okay, so the question is, can you please explain the difference between ML, machine learning based downscaling, and machine learning based simultaneous bias correction and downscaling? So is there a difference? Yashwant.
So when it comes to downscaling, for example, you say you have 100-kilometer output from a GCM, and you're essentially running your hydrological model with 25-kilometer input rainfall data. So you want to downscale the coarse resolution GCM to the 25-kilometer, which you can do with statistical downscaling or dynamical downscaling. And you bring the 100-kilometer GCM data to the 25-kilometer resolution data using your statistical or dynamical downscaling. And at 25-kilometer resolution, again, you will compare. That doesn't mean since you have downscaled, the downscale data will match exactly with the 25-kilometer observation. Again, the distributional errors will be there. At that stage, when you see the distributional error, then you go for the bias correction to match the distribution of the downscaled one with the observations. And recently, instead of downscaling from 100-kilometer to 25-kilometer, the researchers are also interpolating the 100-kilometer GCM data to 25-kilometer and then doing the bias correction and telling this is working better. So I will directly use this as an input to the subsequent models. But physically, how feasible it is should be checked in your region with the calibration and validation before using it for the application purpose.
Thanks, Yashwant. Next question is by Ravi Ranjan. Ravi, would you like to unmute and ask the question yourself? Okay, so his question is, what points to keep in mind while downscaling if the main purpose is to study extreme events?
When it is a main focus is on extreme events, I would suggest refer to some of the papers, and especially if you see a few papers like which is published by Professor Shubhamil Ghosh and others, they have done a kind of regression techniques where they have used two different regression models for greater than 95th percentile of the rainfall and less than 95th percentile of rainfall. And they have concluded that the regression models using for greater than 95th percentile rainfall is able to better adjust the extreme values closer to the observations, and this is the best way to use. And when it comes to the dynamical downscaling, it is a continuous run with the physical model, so there is no separation between the extremes and normal runs. We do continuously run the models. But when it comes to the statistical downscaling, you have different procedures like this. So you can separate the events, you can separate the rainfall days, less than extreme and more than extreme, and you can use your own distributions to fit, or the statistical models to fit.
Okay, so the next question is from Yuvraj Dhivar. Yuvraj, would you like to ask the question yourself? Yuvraj's question is it necessary to have 30 years of data to build a relationship between observed and GCM? So it's about data length. Yaswanth.
Yeah, when it comes to the climatological studies, we typically see the 30 years of data because it will widen, it will reduce the issues with the internal variability and other issues present with the 10 years or 20 years data. As I mentioned earlier, if you say take only 10-year values, the 10 years may be having a high number of El Nino events and La Nina events, and it may not be matching with the climate observations. So that is the reason we typically look for 30-year time period to see whether the mean and other statistical properties of the climate model is matching with the observations. So to reduce the internal variability issues and the teleconnections and other issues, so we usually go for the climatological base period, and it's decided by the WMO that usually the climatological is 30-year time period. So this is the reason we go for 30-year time period.
Thanks, Yashwant. Next question is from Surya Shankar. Surya, would you like to ask the question yourself? Okay, so the question is, what is the most reliable platform to compute and downscale the data?
So the platform, does he mean is he available here?
Yeah, I can see him. Surya, would you like to unmute and explain the question?
Yes, sir. I would like to know about what are the platforms are recently used for computing these types of data, means downscaling the satellite data. How to means which softwares are used? What is the reliable software we can use?
Yeah. So essentially, these statistical models develops upon how you are writing your own codes. For example, if you want to write your own regression equation, building up the relationships, so you can use MATLAB or Python. So any other coding languages to develop the relationships and check the errors and make it further improvements. Or else there are some platforms. So exactly, I'm not able to recollect the name of the platform, but they are directly providing the downscaled outputs. They are directly doing the downscale with their own techniques, and they are just giving the downscale products to the end users. So it essentially depends on how you want to use, but we can't reliably use those products because we don't know how well they have been matching with the observations and other things. So we have to do the error calculations and other things. It also depends on with what observations they are actually downscaling. So the downscaling results also depend on what observations you are using. So if you use a poor observations which are not having good reliable data, so again your model may give a poor projections into the future. So when it comes to the platforms, I would suggest to learn the concepts and use your own coding techniques, or some of the codes and algorithms are available from the papers which the authors are providing. So you can either use the directly downscale products, or you can use those codes to make it in your own way and do the downscaling.
Thank you, sir. Thank you, sir. My doubt is cleared.
Thank you.
Yashwant. So our next question is from Pradeep. Pradeep, would you like to ask this yourself? You can unmute and ask yourself if you want. Okay, So his question is about, again, about data lengths. So in case of data scarce scenarios, shall we use 20 years of data to build the relationships? Would that be okay?
Yeah, in the usual suggestion is should go for 30 years of data. So I think with the recent advancements in the data, so there are many global products which are providing 40 to 50 years of rainfall data, temperature and everything. So we should not be in a position to say the data is not available even for the scarce reason. There are several gridded data sets available like rainfall and temperature. But even if you are going for 20 years, my suggestion is you should compare with you should calibrate and validate. So if you calibrate for 20 years, you don't have the validation point. So I would suggest not to go with the 20 years, but choose the gridded data sets that are available and do the corrections. But even if you say that the data is scarce and you are not able to do, just do for the calibration and check if it is matching well and good, you can go ahead. But this is not a reliable suggestion to do. So use at least 30 years of data for calibration and make it validation for 5 years. And do the data sets are currently available. Many gridded data sets have developed in the last 2-3 years across the globe. So there is an ample amount of data to see that.
Okay, we have a hand raised from the audience from Arindam. Arindam, would you like to ask your question?
Hi, am I audible?
Yes.
First of all, thanks for this such a nice introduction and all. Actually, I was going through this concept a few days back, and it was glad to know this from you people. I actually am having one doubt. You can tell me a kind of silly or not. As you were saying that for the GCM data, as we are using the same IP, if you're considering the data which are providing by the IMD, that is if you're taking simply rainfall and precipitation or the Tmax Tmin data. So they're providing the data in a resolution of 0.25 cross 0.25 degree. So that covers a distance of around 22 to 27 kilometers. So if we're using that data for any kind of research work based on extreme events such as drought or flood, so how much do you suggest that we should go for downscaling from that 22.5 kilometers to below for getting a much accurate result? So what are your thoughts on this? So should we go for a downscaling of those data too, or should we go for the downscaling of the data available with the GCM itself?
So here, for your first question, when it comes to the downscaling of observations itself, for example, the IMD 0.25 degree is a most used data set, and but actually the development of the IMD 0.25 degree data is again dependent on the density of the stations that they have considered. So in certain regions, the density of the stations is very less. So typically from my experience, when I compare the extremes, so for example, if I say, if you go to the highest rainfall that has occurred in Bombay, the 2005, 950,000 mm. But if you see the IMD 0.25 degree data, you will not find, because the interpolation will smooth out such values and you may see the less values. So even if you're trying to downscale the IMD data again to the higher resolution, you need to have a proper independent variable so that the values will be properly downscaled to the higher resolution with magnitudes of such high rainfall. So or else there is no use of again bringing down the IMD data to the normal higher resolution. So we should keep that in mind. And when it comes to the comparisons of GCMs and IMD, so since the GCMs are at very coarse resolution, so typically now, as I mentioned in one of my slides, they're just interpolating to the IMD 0.25 degree with a bilinear or conformal remapping technique or some other conservation techniques to the higher resolution, the IMD resolution. And there, at that IMD resolution, they're actually adjusting the bias using the bias correction techniques. But usually, based on my research reading experience, what I suggest is not to do such kind of bias correction techniques most ideally, because you are bringing a 150 kilometer with a simple interpolation technique to 25 kilometer and telling that I will adjust the bias and it is matching very well and I will project it to the future is not a reliable method. Instead of that, it is better to downscale first and then do the bias correction. So even the recent one of the paper also has found that do the bias correction only if the model and observations resolution mismatch is very less. Say, for example, if the model is having 40 kilometer and observations are at 25 kilometer, it's okay, reasonable. But if the models are at 150 and 200 kilometer and observations are at 25, and still you say I'll bias correct and I'll say these are matching good, that is not a suggestion, and they have proved that that is not a reliable method to do.
Getting it. Thank you so much for the explanation.
Thank you.
Yeah.
We have another question from Munashila. Any other satellite is better than GCM datasets? I'm not sure if it's a question or a comment. But would you like to ask this question yourself? In the meantime, we'll take the next question from Naveen. Naveen, would you like to ask the question yourself, or do I read it? Naveen's question is, it's about CPM products. So do we already have some CPM products covering India, or are they in development for near future? I'm in a common work, so he's in a common working group space, so he can't speak.
Okay. Could you just repeat the question again, Dr. Tejas?
So his question is about CPM products.
Okay.
Do we already have some CPM products covering India, or are they in development for the near future?
So I think CPM, in the sense what he's asking, I feel it is a convection permitting model according to the presentation that we have given. So, but it's something else. I really don't know. But if the convection permitting model
is the same. He wrote it. He wrote it.
He wrote it.
Yeah, please go ahead.
Yeah. So if it is a convection permitting models, the institutes which are having the high computational power are already using to develop the forecasts or the simulations at convection permitting models, that is at 4 kilometer resolution usually we say, or 1 kilometer, that is a high resolution. And already the IMD is already providing the forecast at a very high resolution also, typically at convection permitting scales for few regional centers using their own weather models. So currently the many institutes, due to the advancements in computational power, they are running their own models to develop at 4 kilometer resolution. And probably in the next coming years, it would be a common methods to, with the increase in the computational power and availability. So the people are tending towards the less than 10 kilometer resolution forecast or the model simulations.
Naveen, I hope this answers your question. I can see no other hand raised, neither a question. So I think so we can wrap this talk.
Yeah.
Thank you so much. Thank you so much, Yashwanth. This was a wonderful talk. I learned a lot, and thank you everyone for attending. For future updates, for talks like this, tune into our. Please register to our. There's a form in the chat box. Please register there. Register to the Young Hydrologic Society, and we'll keep you posted about upcoming events. Thank you so much.
Sir, you were telling how to download GCMs.
Yeah. Dr. Tejas, my screen is still visible on the screen?
Yes.
So, so the downloading is in the Google, you just try to type the CMIP6 DKRZ ESGF, or even if DKRZ is not there, the CMIP6 ESGF. So usually the first site will show you the CMIP6 DKRZ, that is the all the data products are available here. So you can just open this.
Yashwanth, we are only seeing your PowerPoint presentation.
Oh, okay. I'll just change the share. So is it appearing now, Dr. Tejasvi?
Yes, it is.
So one can just simply type the CMIP6 DKRZ ESGF. So it will lead to a few of the sites where the data is available. So usually the ESGF is the reliable server where we can download the data. So you can just simply select this website, that's CMIP6 DKRZ, that is at the ESGF node. So once we enter into this page, we have the older products also like CMIP5, CMIP3, and our interest is on CMIP6 search interface. So we can go for CMIP6 search interface here. And so then we will land into the CMIP6 models and to download here. So there are many subsets with different combinations, but when it comes to the applications in hydrology or for the end users mostly, so you need not worry about when they show a single options, you need not select them, it will be fine. So there are many models like EC Earth. As I mentioned in one of the table, there are many models in the CMIP6. It's up to our choice to download all the models or to download any individual models. Or better is, I will suggest there are papers which tell already that a certain Indian region or certain location, these models are showing good outputs or good predictions. Out of 35 models, they may suggest these 10 models. So you can read multiple bunch of papers and get into the final selection of the models based on their suggestions. So you can go with that procedure also to minimize your computational task. So you can select the model. Suppose if I want to download a Merox 6 model, I will select the model here. And then I will go to the, so you need not select any other these things. You can just go for the Merox 6 model. So if we go to the frequency, so usually the data available at sub-daily scale are not that reliable. The data available at daily scale are okay. So I'll go for daily or monthly. So if you want to download monthly, you can just select MON. If you want to download daily, you can select the day. So this is the frequency at which I'm downloading the data. And you need not worry about this really. But if you're too much enthusiastic and to see certain models are given forcings only with natural or only with aerosol. So you need to go with detailed documentation of CMIP6 to see what kind of simulations they have done. But typically we are hydrologists are not interested in this. We need just the final outputs with greenhouse gas emission forcings, the precipitation and temperature and other variables. So if you go to the variable here, so there are many variables here, which already the CMIP6 page will show you what is the full form of this variable. And you can come down and usually the standard names are also given here, the full names of the variables. So these are the variables here. So suppose if my variable of interest is to download the precipitation, so I can go to the precipitation data. So usually in here, we represent the precipitation with the variable name PR. So I'll select the precipitation data. And as I mentioned, the modeling group try to run with different forcings, like what if happens to the state of the climatology with abrupt 2 times CO2 or 4 times CO2 or anything. But the major classification that has done by the CMIP6 is so there are some classifications which are made by CMIP6 like SSP 119, 126, etc. So these are optimistic and pessimistic conditions. The interested readers can take any web page to understand what are these SSPs. So they typically speak about shared socioeconomic pathways. So what if there is no cuts for the industrial emissions and everything? So it is so SSP 245 is a moderate scenario, we say, and SSP 585, 540, 585 is the high emission scenario. So if you're interested to download for SSP 585 and SSP 245, that is moderate scenario, you can select these scenarios. and one for the historical, because you need historical data to compare with your observations. So here hist will represent the historical simulations. So this is a historical one which you need to select. So it will display the models. So you can use the list files to download. So this data is available from 1850 for the historical 1850 to 2015. So if your focus is on 1980 to 2015, you can just go down and select only the 1980. So it depends on the model. Actually, some models provide each 10 years of data. Some models will provide directly 30 years of data. So some models will provide only 5-year subsets of the data. So it's up to your interest to download what data. And as I told, there are ensembles R1, 2, 1, I1, P1, F1. So you can select a common variant label here. Suppose if you are interested in R1, I1, P1, F1, a common variant label. So you can select such variant label here and go again first, and you can click the search button. Then it will display the variant labels only particular to that variant label for the Mirox 6 model. So if you select multiple models along with Mirox 6, I will be getting the other models also. So you can just click on the file, it will download. But I would suggest, like, if you are interested to download multiple files at a time, if you are well aware of the Linux scripts, you can use this wget script. So it will download, it will give you a text file script. So you can use that Linux commands to run this script text file. It will download multiple files. Or else, if manually to download, you can directly click the links here, and the files will get automatically downloaded here. So the more information on the variables will be available on the CMIP6 webpage itself. So typically the precipitation we represent with the PR. So that is a major variable which we select. So this is a typical procedure to select the models. Yeah.
Thank
So
you,
I think
sir. Thank you.
this should be clear, I think. Yes.
Yeah, very nice. Thank you.
Yeah.
So I think we are.
Yeah, I think it's fine now.
So in the interest of time, I think we should conclude this talk now.
Yeah.
If anyone of you have any more questions, you'd like to have more discussion with Yaswanth, please feel free to write to him. He showed his email ID on this last slide, and please just feel free to write to him. And I'll request all of you to please fill the form that has been in the chat box. It has been pasted in the chat box. It's there on our social media handles. Please feel free fill this form so that you're tuned to our future updates and future webinars. Thank you so much. Thank you so much, Yaswanth. Thank you everyone for attending.
Thank you, Dr. Tejasvi. Thank you.